Alrighty, good morning, guys. Can you hear me? Great. Before we get started on today's material, are there any questions? If I bring up the first homework, let me just do that, and then share my screen. The first homework here, which is due next week, next Friday, we've covered most of what is in there. The things that we have not done is we talked about all the things, but we have not talked about this exception rejection algorithm for problem number 3. So that's the part that we're going to start out by doing today. This is why it got delayed. The homework due date got pushed a week, was so we could talk about this acceptance rejection algorithm that is in the first homework. So I'm going to start clearing that up, and then we'll move into characteristic functions. Okay, so that's the plan for today. The plan for today is today's plan. So we're going to start out with this acceptance rejection algorithm, and this is needed for homework 1. Can you turn the volume up? I can try. Okay, I hope that's better. So the acceptance rejection algorithm, that's the first part of today's lecture, and then the main bulk of the lecture is going to be about characteristic functions. And we're going to be spending quite some time talking about characteristic functions, and this here is needed for these stochastic wall models that we're going to be considering in the later on in the course. So stochastic wall models, the way we're going to attack stochastic wall models will be using characteristic functions, and yeah, we're going to spend quite some time on characteristic functions, both today as well as next time. But we're going to start out with this rejection algorithm. Okay, and if there are any questions, just please interrupt. Let's see if we can clear it up. So this is von Neumann. This is von Neumann's algorithm, which allows us to. This is another way. This is another way to generate realizations of arbitrary distributions. I should put in a quote here for Neumann. So, quite famous, very famous mathematician who worked on a number of different things. Some of you might have come across his work. For example, if you ever dealt with the simplex method for linear optimization problems, von Neumann played a big role in that one too. Von Neumann has done a lot of things, and he has also had quite a bit to do with simulation. But he has this. This is a quote. This is a von Neumann quote. He has lots of quotes. But this one here is very important, not very important. This one here is relevant for what we're doing. So von Neumann quote, he has many. If you Google von Neumann and his quotes, a bunch will come up. But this one here is something that you will see often in connection with simulation. And it says, anyone who attempts to generate random numbers using deterministic means is, of course, living in a state of sin. Right, so it serves as a warning. It serves as a warning for using like a computer to generate these realizations of random variables. Right, so this is another way to generate realizations of random variables with arbitrary distribution. Right, so what Neumann says is that this is not really possible using a computer. And I've been reminded of this quote a few times in connection with teaching. Years ago, we were doing a homework problem, and there was one of the students who got different numbers than I did. We tried to figure out. So he was the only one who got numbers that were different than my numbers. The other students in the class got numbers that were similar, but he did not. And so normally then you expect that the student is the one who's wrong. But in this case, we spent time trying to figure out where his mistake was in the code, and it turns out that he actually never made a mistake in his code. The problem was that the software he used to write his code in, that simulator, that random simulator that he used had it had a bias in it. So I remember that was back in the days where sending large files was complicated, but I remember sending him a million numbers, like a million different realizations from my computer, and asking him to run his code using those numbers. And as soon as he did that, we got exactly the same numbers. Right, so it just serves as a warning. I forget what language he was using. I was probably using MATLAB at the time too. But his implementation had no mistake in it. It was the underlying simulator that the software used that had a bias in it. Right? And so this feeds right into Neumann's quote that says that as soon as you try to generate randomness using the deterministic object like a computer, you can't do it. So just something to keep in mind when you're playing with simulation. And this, yeah. So that's one of Neumann's many quotes. It's just something to keep in the back of your heads when you do simulation. Okay, so what is the idea in Neumann's algorithm? Well, the idea is Right, so you have one distribution. You have one distribution which you can easily sample from. For example, it could be the uniform. It could be the uniform. The probability that u is less than u, this is equal to u for any u between 0 and 1. Right, so that could be 1. That's typically the starting point. The one we're going to be using today is the exponential. So we're going to have an exponential. So it's going to be positive. The probability that x is less than x is going to be, it will be this interval from 0 to x. There will be some parameter lambda, e to the minus lambda y dy. I think we can calculate what this here is. This is equal to 1 minus e to the minus lambda x, right? So this here is true for any x between 0 and infinity. So here, lambda is a positive number. And so how can I easily generate, the starting point was we would always do uniforms, but let's just revisit this probability transformation method. So let's recall that u given by f of x is uniform, right? So f minus 1 of u, this is my x, right? So I just need to compute. I need to compute what the inverse is when f of x is this distribution function up here. This is 1 minus e to the minus lambda x. So I need this inverse. This was the probability transformation method that we had talked about. This is my distribution function for the exponential. When I take a uniform, plug it into the inverse, I get the random variable. I get a random variable that has the distribution capital F, right? So I just need to invert. So I'll invert f. This is y is equal to 1 minus e to the minus lambda x. We need to solve for x. So I'll get e to the minus lambda x is equal to 1 minus y. I take log on both sides. I get log of e to the minus lambda x is equal to log 1 minus y. And this is equal to minus lambda x. So I get my inverse, x is equal to minus 1 over lambda log 1 minus y. So this here gives me my x. So I can get, so you simulate a uniform ui, then xi is what? Minus 1 over lambda log 1 minus ui. Then this point here is a realization of an exponential. One can note here that we talked about that last time, that if u is uniform 0, 1, then 1 minus u is also uniform 0, 1. So this, or if you want, you can do minus 1 over lambda log of ui. either one of these two is going to work. Okay, so the starting point is so you have one distribution which you can easily just sample from. Okay, so for example, that's the starting point. Okay, so then what? So that's the starting point. So this is the idea. So you start with a distribution that you can easily sample from. And then you want, so this is idea continued. So you want to sample X, but can only do Y. So this is the idea continued. So you want to sample from X, but you can only do Y. So what are we going to do? Well, we're going to make some assumptions. So the algorithm needs an assumption. Needs an assumption to work. We're going to say that X has density F. So that means that the probability that X is less than some threshold can be calculated by integrating out F. We're going to say that Y has density G. So that means that the probability that Y is less than Y can be calculated by integrating G of, say, A, dA. So those were two assumptions. And the third one is that we can find a constant. There exists a constant C bigger than 1, such that when I take the ratio between these two functions, f and g, f of x divided by g of x is less than c for any x. So just as we shall see, this is a node. So we shall see why you want c close to 1. Right, the assumption is that there is a constant that is bigger than or equal to 1, but we're going to see why you want your constant to be close to 1. We're going to see that at the end. We'll do the algorithm first, and then we have a discussion about this constant c here. You want to sample x, but you can only do y, but presumably you can do many different y's. So which one should you use? Well, you should check this condition here, and then you should find a g that allows this c here to be close to 1. Okay, so we've done a few steps on the idea continue. So now we're finally going to get down to the meat of it. What's the algorithm? So here's the algorithm. This is the rejection. Shouldn't call it rejection. It's accepting, rejecting. Acceptance, rejection algorithm. Okay, so the algorithm goes as follows. Start by generating a realization. realization y of y, right? That was the starting point. You can do samples from y. So start by generating one of those. And the next step is you're going to generate a realization u of capital U, where u is independent of your y and u is uniform. On the interval 0 to 1. Okay, so that's easy enough, right? You can generate a y of y, and you generate a u of capital U. These are independent, and u is uniform. So now comes the crucial step. This is when you get into this acceptance, rejection part of the algorithm. It says if u is less than or equal to f of y, y was that realization up here, u was that random realization of the uniform, divided by cg of y, then set x equal to y, otherwise return to 1. So this is how you do it. If you want to generalize, you want to sample, you want to sample x, but you can only do y, right? So you need a realization x of capital X, but can only generate y of y, right? So how do you get your hands on an x when you can only get y? Well, this is what the algorithm says. If you are willing, so the starting point is we can do these uniforms that are independent, right? So you take the y you can do, you take the u that you can do, and then you test here with this criteria. And if the criteria is satisfied, then you get your sample little x. Otherwise, you don't get anything, and you have to go back to 1 and do it again. Questions so far? Okay, so when you code, you probably want to use, you might want to use a while loop. Right, because you don't know how many times, if, for example, so if you have to, to generate, say, 10 samples, you don't know, a priori how many loops you need to go right to generate 10 of these points, these x points. You might have to sample in this algorithm here many more times than you might have to sample through these 3 steps more times than just 10, 20, 30 times. And this is why this constant c has to be chosen close to 1, because that that constant C is what will control how likely it is that you have to sample through the algorithm one more time. So we'll see that in a little bit, but you can see that C here, plays a role. Right, so often we'll write code using for loops, but here you might want to use a while loop. Are there any questions or comments on the algorithm before we do the proof? So the proof is not it's not terrible. So a proof so what is it we're doing? We're looking at accepting, so that's the probability that the random variable y is less than y, given what? Given that the uniform was less than that threshold f of y divided by c g of y. We want to prove that this conditional expectation here, this is the goal, that this is somehow miraculously equal to the probability that x is less than y. Okay, so this is what we have to establish, the probability that y is less than some number conditional on this ratio. This is exactly the same thing that the probability that the random variable x that we are hunting is less than that number. Okay, so let's try to do this. The first part here is a conditional probability, so we compute this as the probability y is less than y and u is less than f of y divided by c g of y. And then we have to remember to divide by the probability of the thing we're conditioning on. So we have to write a line here, divide by the probability that u is less than f of y divided by c g of y. So we have to prove that this ratio becomes that probability. Any ideas on how we should proceed from here? We have a random variable y, and we have a random variable u. What do I know about u and y? Well, I know what u's distribution is, I know what y's distribution is, and what do I know about their common distribution? I know the marginals, do also know the common. Well, then you go back to the algorithm. So y has a density little g, x has a density little f, u is uniform, u is independent of y. So this is the key here. We're going to be using that they are independent. So how do we compute something like this when they're independent? So we're going to use the independence lemma. Do we all remember what the independence lemma is about? Does anybody remember what the independence lemma is about? It says that if I take the expectation of a function, in this case is y and u, and I condition on, say, y, how do I compute this? Alice says you can pull out the stuff that's independent. So you got a y here, we're conditioning on y, and then this thing here is independent. Right? So we take the y, we replace the y by a dummy. Let me call that dummy for, I cannot use the same symbol as the one up here, so I'm going to call this a y0. And then we take the u, keep him there. And then I compute the expectation. No conditioning. When I'm done computing that expectation, I replace the dummy by the random variable I'm conditioning on. So this is the independence lemma. Okay, so we're just gonna make a little note like that. We're also gonna use iterated expectations. That's the other step. So if I have my conditional expectation, so let me just use the same thing as above. If I compute the expectation, right, that's my conditional expectation. If I take the expectation of it, right, so the expectation of the conditional expectation, this is gonna give me, right, so the iterated expectations is this one. The expectation of the conditional expectation is equal to the expectation of the random variable I'm conditioning on. This was what we had talked about. This was the unbiased estimator. Right. I'm thinking about this conditional expectation here as being an estimate of f of y comma u, given I know what y is. So that's an estimate. It's unbiased because the estimate, when I take the average of it, I'm going to get exactly the same thing as when I take the average of the thing I'm trying to estimate. So it's an unbiased estimate. These were things that we had used in 6.2.1, and now we're going to use them again. We're going to work on these two probabilities. We have that ratio. So what do? We write out the probability that, let's do the top one first. The probability that y is less than y and u is less than f of y divided by c g of y. How would we work out what that is? Well, we start by using iterated expectations. So a probability, right? That's the indicator. That's the indicator that y is less than y and u is less than f of y divided by c g of y. So these two things are the same. And then I'm going to condition. I'm going to condition on y. And then I'm going to take an extra expectation. Okay, so the probability is just equal to the expectation of the indicator of that set. And then I'll take the conditional expectation and then the expectation, I get back to the original one. Okay, so here I have the situation that y and u are independent, so I can use the independence lemma. I'll write this here as I replace the y by the dummy. This was y0 less than y. And u less than f of y0 divided by c g of y0. Then I take the unconditional expectation of this thing, and then when I'm done, I'll replace the dummy by the random variable. So we should just note here that this quantity fy divided by cgy, let's just make a note here that this quantity here, f of y divided by cg of y, how big is this? Well, I know that the assumption was, right, that the assumption was that I can find this constant c such that this is true. So when I divide c over on the other side, I'm going to get something here that's less than 1. So this here is a number between 0 and 1. So u less than or equal to a number between 0 and 1, I'll use that as uniform. So I just get that, well, the first one can go outside. So this is y less than little y. And then the probability, u is less than this number. That's just going to give us the number. So this will be y is replaced by capital Y divided by CG on capital Y. Right, so let's go over it again. An expectation this year has nothing random in it. It can go outside. It'll just be the indicator for y less than y. And then you have the expectation of an indicator that u is less than this threshold. U is uniform, so this just gives me the probability that u is less than this ratio. U is uniform, so it just gives me this ratio, and that's the one I put here. I replace y0 by y, and I get this quantity. And then I can use that. I know that y has a density, so I can integrate here. Y has density, so I'm going to integrate from minus infinity up to little y. That's the first part. And then I'll have f of, say, a divided by cg of a, multiply onto y's density. What was y's density? Y has density g, so I need a g there. I multiply here onto a g of a, dA. And this all becomes an integral from minus infinity to y. The g's cancel. I get 1 over c f of a dA, which is 1 over c, and then f was the density for x. This is the probability that x is less than y. So we're getting closer. At least we got something up here. That looks familiar. We have a 1 over c, but of course this was only one part. The other part we have to calculate. Is what is downstairs. Let's try to calculate what's downstairs. The thing that is downstairs is, so we compute p of u less than f of y divided by c g of y. So we will use the same tools as before. We will use real condition and then take the expectation. So the probability of a set is equal to the indicator that u is less than f of y divided by cg of y. And the null condition on y, and take the expectation. Okay, so we'll proceed as before. We have u and y are independent. U and y are independent, so I can use the independence lemma. It says you take out what you condition on, replace it by a dummy, divide by g applied to the dummy. When I'm done computing the condition, when I'm done computing the unconditional expectation, I replace the dummy by the random variable that I was conditioning. So it's a very similar situation to before. What I have here is the expectation of an indicator. Okay, so that's the probability of the set. Really, this is taking us way too far. Yeah, could have skipped all these steps. I could just have written this thing out here. Well, never mind. Let me do it this way. There are many ways to do it. What I'm doing here is absolutely not the easiest one, but nevertheless, this is the probability. This is the probability of the set. U was uniform. This is the number between 0 and 1. I'll get f of y divided by cg of y. And then I'll use the fact that y has density g. This is an integral over r of f of a divided by cg of a times the density g of a. And again, it will cancel out. I'll have 1 over c integral over r of f of a. But f is the density, so this here becomes 1 over c. And now we can combine the two expressions. Right, so I now have calculated what this thing here is equal to. What was downstairs was 1 over c. What was upstairs, that was what we just did. What was upstairs, what we had on the previous slide, 1 over c p of x less than y. Now, of course, you'll cancel out. The constants. I'll just get p of x less than y, and this is what we wanted. So the algorithm works, which is, of course, otherwise you wouldn't look at it. So maybe we should look at this constant. Why is it we want this constant to be close to, why do we want the constant to be close to 1? So why do we want to have the constant close to, why do we want the density we could sample from was the density we could sample from was y, so we can sample from g. Okay, so why do we want g such that if of x divided by g of x is bounded by c, with c bigger than 1 but close to 1. That's the thing that we can sample from. We want this ratio here to be bigger than 1 but close to 1. Well, we know, one thing we just did from the proof we saw that the probability that u was less than this threshold, f of y divided by c g of y. We calculated what that thing was. Find it. It's this one here. By that probability, we calculated it to be 1 over c. So I could call this here for p. Right, this now is going to be a number between 0 and 1. Right, so the probability, this is exactly the probability of termination. Right, this is when the problem, this is when you accept. This is the probability of acceptance. Right, that was in the algorithm. That's when you terminate the while loop. That's when you accept. This is when that ratio is when the uniform you get out, when it's less than that ratio, this is when you terminate. Right, that's when you terminate your while loop. So if you want a high probability of acceptance, then you would want to have your c to be close to 1. Another way you could do it is we could calculate the expected number of loops. Calculate the expected number of loops. So say what's the probability of 2 loops? Probability of, say, 2 loops. Well, then if there's a probability of 2 loops, that means that the first time around you're rejecting. So that means that f divided by cg of y, u is going to be bigger than that, and then the second one you're going to accept, so that's going to be less than f of y2 divided by cg of y2. So this is going to be they're all independent. So this is going to be, the first one is going to be 1 minus p, and then the second one, this is going to be p. We could move on to saying the probability of 2 loops, probability of 3 loops. The probability of 3 loops, and then you would have to have the probability, the first one, you would have to reject. So this is f y1, cg of y1, and u2 is also going to be rejected, so that u2 is big. And then the third one, this is when you accept. So that's going to be less than f of y3 divided by cg of y3. And what will it be? It will be 1 minus p, 1 minus p, and then this one here has p. So this is 1 minus p squared times p. And of course, you can continue the probability of, say, n loops. It will be 1 minus p to the power n minus 1 times p. So now we know what the probability distribution is, and then we can compute the expected number of loops, well, I'll just take the average of this distribution, it'll be the probability of getting n. So that will be n times, and then the probability will be 1 minus p n minus 1 times p. And then you sum. And if you do this, you're going to get 1 over p here, and this is exactly my c. So again, you want the expected number of loops to be small, so you want c here to be as small as possible, so you want it as close to 1 as you can get. Any questions on some of the calculations we've been doing here? Maybe if we do an example, it'll be a little bit clearer. So we try to do an example, and then we'll see exactly what this constant c here is going to be. We do an example. We're going to say say c is standard normal. Right. So that's the probability that z is less than a is this Gauss function integrated from minus infinity to a e to the minus y squared over 2 dy. A is in R. So if I look at the absolute value, and then this has density so this is f of x. Let me write out what the density is. 2 divided by square root 2 pi e to the minus x over 2. And this is for x positive. Because absolute value is, of course, a positive random variable. But you want to sample, so you want you want to sample from this guy's distribution using the exponential. And the exponential was this e to the minus x that we had before. This was the exponential from before. Where I put lambda just to be 1. Right, so we know from before that we can sample from the exponential. From the calculations that we did, we can sample from the exponential, simply just take a uniform, plug it into this formula, and you're going to get an exponential. So we can sample from an exponential. If I can sample from an exponential, how can I sample from the absolute, from this distribution, which is given by the absolute of a normal? Okay, so what we have to do is we have to look at this ratio. So we have to look at this ratio, f of x divided by g of x. That was the ratio that was crucial. This is the ratio we want to be bounded by something close to 1. Right, so this is 2 divided by root 2 pi e to the minus x squared over 2. Right, that was the top part. And then the bottom part is going to be e to the minus x. Right, so we can write all that out. 2 divided by root 2 pi e to the minus x squared over 2 plus x. Is this thing bounded? And yes, it is, right? Because x squared is going to grow faster than x, and it has a minus sign. So this thing is bounded, but how big can it get? So if I maximize what's inside here over x of minus x squared over 2 plus x, what is that equal to? I'll take the derivative and put it equal to 0. So this is going to be minus x plus 1 equal to 0. This is going to give me that x is 1. So then this maximum here is going to give me minus a half plus 1. This is equal to a half. Okay, so I'll plug that in up here. This is 2 divided by square root 2 pi e to the half. And if you plug this into a computer, you'll get something like 1.31549. Right? So is that close to 1? I don't know. It's not too big. So what you're expecting here is to perform 1.3 loops to accept. And so if we adapt the algorithm to this specific example, it'll be the first one is to generate y, and this is so you can use that formula, which is y is equal to what was it, minus log of ui uniform. So that was the first step. Then you're going to generate UI. These are different. So maybe I should say a V here so we don't get these mixed up. These are not the same. So I'm going to say V here. Generate UI. This is also uniform on 0, 1, and independent of yi, and is V. And then you do the check. The check is if UI is less than if UI is less than, so here we had f of x, it should be less than. So what are we doing? We're checking this thing here gets to be divided over. We're checking that this is less than f of x divided by, oh gosh, it's a mess over there. So this is 2 divided by root 2 pi e to the 1/2 times g. Then we can write all this stuff out. This is e to the minus x squared over 2 plus x And then you have minus a half. And this is not a u, this should be a y. I'll just check, what was it? I'm messing up the symbols here, right? I have a y and I have a u. I should only have u's and y's here. Just go back, make sure I didn't mess this up. Right, so we're checking u, so we should have a u here, and then you should have a y. It should not be x's, these should be y's. It should be y's. Too much copy paste. If this is holding, well then the absolute value of this CI, you can pull that sample as yi. Otherwise, so check if this is true. Otherwise, back to 1. So this is how you'll generate samples of the absolute value of the normal distribution. Yeah. Are there any questions or comments on this part? So again, when you loop around in this algorithm here, if you get down to here and this one here fails, you're not going to get a realization. You'll have to go back and redo it again and then hope that this is going to work. And if it doesn't work, you have to loop back and go through it again. Right, so we want to just note each loop may not give you a realization of this absolute value of z. Like the probability of getting that is 1. This here was our constant c. So the probability of getting one getting such realization is equal to, that was the one we computed. That was p. This was 1 over c. This is 1 over c. This is equal to 1 over 1.31549. Right, so this here is less than 1. And this is why I'm suggesting that you use a while loop when you write your code. Are there any questions or comments on the acceptance rejection algorithm of von Neumann? Any questions? Okay, so we're going to take a little break soon, but let me just, the next thing that's coming up is going to be these characteristic functions. And I posted the next, homework up there. And the next homework is full of characteristic functions. So I'm just going to show you the homework. It's homework number 2. And all the problems in homework number 2 is about characteristic functions. And I put some of them. We're going to be doing parts of at least the first problem here in class, but we're going to be talking about this today and next week. But here you can see there's just a stack of problems related to the characteristic function. There's a little bit of simulation down here at the bottom. These antistatic variables that we had talked about last week. There's a bit about them in here too. But the first problems, they're all about characteristic functions. So this is what we want to be starting on now. But you can already, at this point, you can already solve the last problem. And this last problem is one that has to do with coding. The first problems are going to have to do with just theoretical questions. So this is what we'll be doing after the break, and this is what we'll be doing next week too. These characteristic functions, they are needed for lots of things, but what we're going to be using them for in this course is going to be to study these stochastic volatility models. And this is going to come later. I talked to Triet Pham, and he says that just yesterday, you guys did material related to ethos lemma. So I know that this is new to you guys, but we're going to be using looking at some applications of ethos lemma already today on how to use ethos lemma to compute these characteristic functions. So I'm going to take it slowly, of course, but it'll give you an idea about already now that ethos lemma is really important. And in this course, you're going to be using ethos lemma to get these characteristic functions, which you can then get into a computer, and you can get numbers out. And without ethos lemma, it will be I don't know how to do it. I'm guessing it's possible, but it will be difficult. Okay, if there are no questions or comments, I propose we take a little break, and then we get back together in like 10 minutes or so. As usual, you need to use a different Zoom link, but okay, let's take a little break and then get back together on a different Zoom link.